Indeed, this year we have 2 awardees for the Pisharoty Awards, and just sharing this with a person who is known as the Marathi Kishorda. If you remember, from a couple of years ago, he was the dawn of IITM. Shivsai Ajit Dixit, who joined IITM at the same time as me in 2012, is the recipient, the co-recipient of this award. Shivsai has been working on some very interesting lab experiments. He's actually set up the Fluid Dynamics Laboratory in IITM, which is probably the best of its kind in the country, and definitely the only of its kind within the MOES institutions, and they've been doing some pretty exciting lab experiments which you'll hear about. He's also been extremely active in the KIPEX campaigns, and he's been traveling to Solapur quite a lot to do some field observations over there. So I'm assuming you'll give a little overview of all your work, Shivsai, please.
Thank you, Anup, for those kind words. How do I make it full screen? Yeah. Okay. So, I've put slide numbers, but I have not put the end slide number. Okay. you won't have many slides. Anyway, so. We have been doing some unique studies at IITM. I would call them as more like fundamental studies on turbulence, wall turbulence. And we have a small lab which was established around in 2013-14, and it's called Fluid Dynamics Lab. Earlier there was a proposal of calling it as Geophysical Fluid Dynamics Lab, but I turned it down by saying that it has a different connotation. So these are the people who are associated with me in the lab. Of course, Dr. Tara is the project director, and so the outline is I would just spend a couple of slides on how the lab was conceived and developed. So that's from 2013 to 16. And then I would come quickly to the scientific research that we have been trying to do. I would summarize them that as 3 points. So we have done some work on turbulent wall jets. Then we have done some work on scaling of drag in wall turbulence as general, and how those results can be translated to the scaling of drag in surface layer fluxes in atmospheric boundary layers. So Sukanya started with clouds, then Jasti took it to planetary scale. I am bringing it down again to process level. Okay, so this is how the lab looked while it was getting constructed. All rubble, foundations for the columns were being laid. And then in 2014, it was inaugurated by the director then, Professor Goswami. And you can see that person with turban there, that's Manmeet Singh. So he was doing a project with me that time. And we had this small demonstration of a rotating table where we could illustrate Taylor columns and Ekman layers and so on. By the way, this team of workshop has been phenomenal for our lab, because any lab requires a lot of support from workshop people, and they have been really phenomenal. And this is how the lab looked when it was inaugurated. So it was just empty room and with a small table there. And this is how it looks now. Okay, so it's well populated now, so much so that we have given a proposal for expansion. Right. So this is the setup that we have developed. I'll talk more about that. This is called as a wall jet setup. So you basically have a settling chamber here, and a jet comes out from this chamber, and it's a two-dimensional jet, and that jet comes out over this plate. So it's a jet which is flowing past a solid surface or a wall. That's why it's called wall jet. Now this particular flow is of, it turns out that it's of interest to us, meteorologists and atmospheric oceanic scientists. In the blue color here, what you see is the PIV equipment. These are the two guys who are there with us for more than 6 years now. Abhishek, he recently defended his PhD thesis, and Harish has been with us for more than 6 years. And that Skypex team, we were having Dasara Puja with masks on in 2021. And this is another oil film interferometry. I'll talk more about that. So as Anup said, FDL actually has state-of-the-art equipments for measurements in laboratory. So we have a hot wire anemometry setup, then we have high-speed and low-speed PIV measurement systems. All these are like, on the wish list of any fluid dynamics laboratory person, and it's a good fortune or great fortune that I have all these here in IITM. Right, so let's come to the scientific point, which is the first one. It's about wall jets. So why do we care about wall jets? Wall jets have been known. The figure on the right is the typical wall jet in laboratory. So what you have is a nozzle. This is the side view of the setup. So you have a nozzle, the flow comes out with speed uj and it develops on this flat plate. And the flow looks something like this. You start from the wall, move perpendicular to that. The flow velocity increases, passes through a maximum and then drops. Now on the left side, this is a typical wind speed profile from Solapur radiosonde measurement, okay, observation. This is taken during July 2018. So this is our famous monsoon low-level jet, as you can see. And the visual correspondence between these two is very intriguing. We started with this sort of intuitive idea. I mean, of course, in the atmosphere you have all sorts of other complications, like you have stratification, you have background pressure drop in the vertical direction and so on. But even as a basic or lowest order model, we started looking for evidences in the literature. Has somebody pointed out anything on wall jets being related to low-level jets? And interestingly, we found that in 1993 and 95, a very well-known mountaineer meteorologist, Smedman, she commented in her papers that the low-level jet profiles, not just the mean velocity or the wind speed profiles, but even the turbulence kinetic energy budgets, the profiles of those, they are very closely resembling the wall jets. But apparently, this idea was not pursued after that. So we could not find any literature after that which actually connected wall jets. And even in fluid dynamics community, lab fluid dynamics community, wall jet is not as popular as boundary layers, pipes and channels, because those flows have a great deal of applications, but wall jets have very few applications. So we started looking at wall jets from this viewpoint, from a very new viewpoint of atmospheric flows. So this is our wall jet setup. As I was telling, this is the photo from a different angle. You can see that the PIV experiment is going on in this. The laser light is shining from the top in the form of a plane sheet of laser. And there are 4 cameras here which are looking at the plane. These 4 cameras are mounted side by side to give you a long field of view, so that we can see larger structures in the flow, which are otherwise not possible if you have just one camera to see. The same setup without the laser is here. Okay, you can see, and this is the close-up of the camera, then how the cameras need calibration, because the cameras are just pixels, right? You need to know what is the distance between the 2 pixels. It is seen. Yeah, so the first publication from the lab actually came out in 2020 in the form of a Journal of Fluid Mechanics paper by Abhishek for his PhD. And it actually answered 2 very important questions in laboratory wall jets. So the first was, before us, people were claiming that the momentum flux which is coming out of the nozzle is the controlling parameter for the wall jets. But conceptually this had a problem, because if you say that something at the nozzle is going to control the flow downstream, then you cannot simply have a self-similar development. And what if the flow goes very far away from the nozzle? Then how will it develop? Will it still remember the nozzle? That was the conceptual point. So the data finally showed that it's not the nozzle momentum flux, but it's actually the local momentum flux. The momentum flux at every location, that actually becomes a scaling parameter. It determines how the flow is going to evolve. And of course, the second point which we tried to address is very relevant to us, as I will show later. Of course, this line is important. We use this thread to get to the heaven. I'll show what that means. Um, so the second point is, even in laboratory fluid dynamics community, people used to think that the region below this velocity maximum is like a boundary layer, and the region above that is like a jet. Okay, that was the conception even in laboratory fluid dynamics. But there were issues with that. Okay, the first issue is that below this velocity maximum, there exists a region of counter-gradient momentum diffusion in wall jets. Now that is something which is simply absent in boundary layers. So how can this lower part be like a boundary layer? So even in laboratory fluid mechanics, these were the questions. So what we found was that the data actually don't support this kind of a picture. Lower part like a boundary layer, upper part like a jet, half jet. It doesn't support. So what is the picture that emerges? The picture is that it's basically a jet which is going along the surface. But if the jet goes along the surface, then it would violate the boundary condition at the surface because it has to be no slip condition. So there it develops a layer near the wall. It's called wall layer. And it's the jet and the wall layer. That's it. That's the story. There is no boundary. Okay, that's what emerged from this paper. So the conceptual picture is like this. So this is the traditional way of looking at it. Boundary layer and jet. This point here up, Umax by 2, you can imagine this to be the height of the jet, a characteristic outer length scale. So I would call it as delta, to be just precise and short instead of z top. So this is the picture that we came up with. It's actually a jet which is going past a wall, but it would have a slip velocity. So you have to have an inner layer, and the jet layer overlaps with that, and you have an overlap which is essentially a non-inertial overlap. So in boundary layers, whenever you say log is there, mean velocity variation is logarithmic with height. What it essentially means is that you have an inertial overlap existing between inner and outer scales. So in wall jets, we simply found that there is no inertial overlap. It is just a meso overlap. And whereas in the boundary layer, you would have an inertial overlap. So this is again a contrasting point between wall jets and boundary layers. So how does it matter for us? So what I've shown here is, these are the plots taken from Dr. Madhu's paper. As you can see here, these are the typical radiosonde derived quantities, and this is the low level jet, and this is the jet core. And as you can see, the inversion in the potential temperature is sitting just below the jet core. Now this is very well known and typical. I've just shown it here. So the idea is that the boundary layer, the atmospheric boundary layer, when the low level jet is present, the atmospheric boundary layer actually extends almost up to the wind speed maximum. Okay, this is something which has been known. Now in view of what we have seen, now the question would be, this sort of a boundary layer, if it is sitting below the monsoon low level jet, will it behave in the same manner as it would otherwise without the presence of low level jet? Okay, that's the central question. In other words, is the jet going to do something more to the turbulence in the boundary layer? So we started attacking this problem in the lab, of course, in the setup of lab. I'm sorry, this red color is showing here as black. Okay, I'm seeing it as red here. Probably Jasti was also doing the same. Okay, so you can see these are the results from PIV. So this is the PIV velocity field, 4 camera fields stitched together, and now we are able to see almost 5 times the height of the flow. So if delta is the height of the flow, then 5 times delta is the field of view length. So we can see the long structures which are of 5 times the length of the height of the flow. Here you can see some hot wire anemometry spectra. So on y-axis there is wavelength, on x-axis there is distance from the wall. So you can see that there are 2 modes happening. So closer to the wall there is a classical mode called wall mode, and you have shorter wavelengths present there which are viscosity dominated. But in the outer part you have the strong jet mode present, and a lot of energy is carried by that mode, and these wavelengths are actually long. They are typically of the order of 2 to 5 delta. This is what we got from hot wire, Then we designed our experiment in such a way that we can capture the 5 delta, the window. Now what you see here is, PIV gives you data in a plane. So it gives you the U component as well as the W component of velocity. So you can have now U prime and W prime both. So after doing this, we plotted the co-spectra of U prime, W prime, much similar fashion as this. What is important is, close to the wall, you have this secondary peak here, okay, which is at long wavelengths. So what it means is the turbulent shear stress in the near wall region is contributed significantly, you have a peak here, is contributed significantly by the wavelengths which are long, which are not characteristic of the wavelengths if it would have been just a boundary layer. So the wavelengths of the order of jet are contributing in the near wall region. That's a surprise. And of course, if you want to relate it to the dynamics, you plot the spectra of the force, which is the dz of Reynolds shear stress. So you can see that these long wavelengths are actually causing some deceleration in the flow here, okay, as seen by this blue color. So these long wavelengths are decelerating. So the point is, we are setting out with this idea, but then what are the evidences that we have? So all these evidences try to tell us that we are seeing something in the near wall region which we should not be seeing if we say that it's like a boundary layer and that outside is like a jet not interacting anything. So again, this is a similar thing. So you take a near wall region and then you see the signal, you decompose it and keep only the low frequencies. You see this 5 delta mode, and the next mode that you see is 2.5 delta. Okay, so these are the long wavelengths. These are characteristic of the jet. These are the same thing, but you do the correlation coefficient analysis. And of course, when you decompose the hot wire data now using these 2.5 delta as threshold, what you see is these are the total. So on the y-axis there is streamwise TKE, and on x-axis it is distance from the wall. So you see that this near wall peak, it's very close. It's Z plus of about 15. Okay, but even at the near wall peak, almost 50% of the energy is actually contributed by long modes. So it's not something which is negligible. It is contributing very significantly. Then we started saying, okay, these are the contributions, fine, but what is causing all this? What are the structures present in the flow which are giving rise to such contributions? So as you can see, this is the velocity. These are the velocity vectors plotted over the contours of U, stream instantaneous velocity, and then what you do is you subtract a convection velocity for the structures through all the velocities. You just Galilean transform the things, and then you will start seeing the vortices which are getting convected at those velocities. So as you can see here, these are the vortex packets. Okay, this is a big vortex packet. There are a lot of vortices, anti-clockwise, counterclockwise in this case, because the mean shear of the jet is supporting counterclockwise vorticity. So you see these counterclockwise rolling motions, and all of them are they are appearing after subtracting a convection velocity. It means that all these are getting convected at the same speed. So it's a packet which is traveling. So this gave us some idea of what is happening. Then we said, okay, what are our results? This is just one realization. Are our results statistically robust? So there is a technique called linear stochastic estimation. Basically, it's a conditional average that you do. So if you take the outer, so this what this figure shows is a linear stochastically estimated velocity field based on a certain condition. So what is the condition? In the outer region of the jet, you take a height and then demand that the vorticity there should be counterclockwise, okay, or the rotation should be counterclockwise, and just condition it based on that. And you do this only for those images in PIV when the long mode in the jet was present. Okay, so that's what is written there. So it's a conditional average, but only done for those images when in the flow when that long mode was active. So when you do this, you see something very interesting. There is of course a counterclockwise rotation here. That is obvious because this was the condition. What is not obvious is this. This horizontal line indicates velocity maximum. Okay. So below the velocity maximum, there is a clockwise counterpart of this anti-clockwise. Now this is something which is very surprising, and it is very robust. We have checked it over range of Reynolds numbers in our setup, and this is a very robust thing. And this is coming mainly from those long wavelengths. Okay, so what is the structure of the long wavelengths associated with the long wavelengths? So the structure seems to be this anti-clockwise vortex outside and the clockwise vortex inside. Okay, and these sort of vortices are very well known in free jets. If a jet is free, there is no wall, then it is well known that you have vorticity of this sign and then you have vorticity of this sign, and they are not one above the other or below the other, they are staggered in X direction. It's well known. So that same structure seems to be preserved here. Okay, so so the point is, the lower part is not like a boundary layer, regular boundary layer. I don't want to go into the details of this, but same thing you can demonstrate using quadrant analysis. So quadrant analysis is a technique where you plot the Reynolds shear stress into various quadrants, and then you start looking at that. This figure I want to tell you something about. So this x-axis, I'm sorry, there is no label for this, but this is the distance from the wall, and this is the Reynolds shear stress, and this yellow curve, this color is yellow. Okay? This yellow color curve is the Reynolds shear stress profile, and this is the location of the velocity maximum. So as you can see, below the velocity maximum, Reynolds shear stress crosses 0 here. So from this blue line to this line, this is the region of counter-gradient diffusion. And if we break this sort of a quadrant into two parts in the counter-gradient region, this quadrant is typical of jet, and this quadrant is typical of wall flows. If we break this into these two, then the addition of these two actually makes it symmetric, and that is the reason this counter-gradient region is happening. So the point is, again, because there is jet presence below the velocity maximum, the diffusion is actually counter-gradient. There are other aspects which are being studied right now. There is something called amplitude and frequency modulation. So these large-scale structures will cause certain modulation of the near wall flow. So if a large-scale structure is passing, it may amplitude modulate or frequency modulate the signal near the wall. So as you can see here, this is a low-speed event happening, and you can see that this yellow curve is kind of stretched out. So its low frequency content is more here. Okay, whereas if you go to this part where there is a positive high-speed event is happening, then it is more frequency modulated in terms of the high frequencies. So frequency modulation is present. So all these are the evidences pointing towards this idea that in a free jet you would have a structure which is counterclockwise and clockwise with a tilt here, and if you have a wall here and if you bring it close, then what will happen is this part will not die. That's the point. It will survive, and that is what is happening. It's getting survived here, and it's crammed into a small region between the wall and the maximum, but it is still there. And suppose if something similar is happening with monsoon low-level jet, then what would happen? That's the food for thought. Okay, so this is what we did, and of course then the scaling idea of momentum rate that I talked about, the local momentum flux, we extended that to laboratory boundary layers. This was not done before. Nobody actually thought about momentum rate in boundary layers. So we actually did that, and this was published in 2020 in Physics of Fluids. So we came up with this sort of a new scaling of drag in laboratory flows, where we said that the friction is to be made dimensionless using new scales, and the Reynolds number should be defined in a new way. And we actually came up with a model. Okay, even in laboratory flows, this model was not known. This is a new model. So what it gives is basically on the right side you have Reynolds number. You just plug in the Reynolds number on the right side. On the left side you will get friction. You will get the answer for friction in your flow. So we demonstrated it in laboratory boundary layers. Then we did some work on pipe flows, which I will skip. This was mainly done in lockdown period. Everybody was locked down. I was at home. What to do? I cannot do experiments. So then we started thinking about how to apply these ideas to other flows. So we applied it for pipe flow, but I will zip through this. This is a very important thing which started after the lockdown. So the idea now is, okay, we have momentum rate scaling newly proposed for boundary layers. Can it be extended to include other flows? And more importantly, is there a dynamical basis for this, or is it just a curve fit? Because otherwise people would say, oh, it's just a curve fit. So we actually did a lot of theory work, which is not shown here, but from the Navier-Stokes equations, we started deriving through the kinetic energy arguments, and finally the same scaling was derived from the governing equations. Okay, so then it gave a very strong foundation for that. And it turns out that this sort of a derivation is not dependent on the boundary conditions of the flow. So any turbulent wall-bounded flow will have this kind of a scaling because it is completely dependent on the cascade of turbulence. It doesn't have to do anything about the boundary conditions. And the boundary condition effects would then come as an add-on. Okay, you just have to top up your dynamical scaling using boundary condition effects. So this is what we did. So we checked that the individual scaling works individually with pipe flow, in channel flow, in boundary layer separately, but you cannot club them because the boundary conditions are different. Now if you take into account the effects of boundary conditions, you have to do a coordinate transformation for that. Okay, and if you do that, the same model can actually be used with the boundary condition effects now thrown in. And so these are accounted by using the shape of the velocity profile. I won't go into those details. But this is what you get. So these are around 88 data points coming from variety of experiments in laboratory boundary layers, pipes, channels, and this is our scaling, and it actually predicts friction with a good accuracy, almost comparable to any laboratory measurement technique. Then we became more ambitious. We said, why just boundary layers, pipes and channels? Let us include all sorts of laboratory flows. Because there are other types of laboratory flows, like flows in pressure gradients and those over the aerofoils and strongly decelerating, accelerating flows and stuff like that. Supersonic and hypersonic boundary layers. So we took all these data sets and if you plot it in conventional scaling, you simply cannot do anything about this. There is no predictive value. The data just appear all over. But the moment you switch over to our dynamical scaling, the basic one, without any top-ups, the data, somewhat, they come along the line. This is the model, of course. But if you see the predictions using that model, you see that, of course, there are large deviations because the boundary condition effects are very important. The moment you throw in the boundary condition effects, the collapse improves. Okay, the shape boundary condition that I told just now, the collapse improves and the scatter reduces in predictions. But these points are still outside. So what do we do about this? These are actually these very strong pressure gradient flows. So pressure gradient has still not been factored in. So now we want to factor in the pressure gradient also. So there is another transformation proposed, and when this comes in, all the data come on one line and the scatter comes within the limits. So this is actually a unification, sort of unification happening, coming from a dynamical understanding that the skin friction or the wall friction should obey a certain scaling, and that has to be corrected for using boundary condition effects. This is the main thing. Now, why am I saying all this? Of course, this is the physical cartoon. This is what it means. So you have the turbulence structure, and the basic dynamics will influence friction. But of course, the boundary conditions will influence the large eddies of the flow, and those large eddies, because they contribute separately to friction, there will be certain effect coming from the boundary conditions into the friction. The cartoon. So we became even more ambitious. We said we have to apply these to atmospheric boundary layers. Okay. So we took Kaipex data from Mehboob Nagar and Solapur campaigns. Now what do we need in all this? From the data, what do we need? We just need the profile of wind speed, so which we got from the radio sound observations. It's not mean wind speed profile, but still it's good enough. And we need the surface layer flux measurements. So we took those from the co-located tower observations. And we plotted this scaling, the basic scaling. So without correction effects, okay. This is the basic scaling, Solapur Mehboob Nagar data. And what is written here is, this is, I'm calling this as NC model. NC stands for non-convective. There are no convection effects here, okay. Just the lab model taken and applied here. But you see that, there is reasonable scatter. But if you start predicting the values using the fitted model, okay, then you see a much bigger scatter, and these lines represent certain error bands like plus minus 40%. Of course, the measurement of U star itself in atmospheric boundary layers is, it's known that it is error prone and it has larger uncertainty compared to the lab experiments. It's of the order of 20% or so. So this 40% is not very bad, but still the scatter is actually too much. But there is something into this. Then we said, what about convection? Because all these flows contain a range of stability values. So the Bukov length going all the way from, these are convective and near neutral cases, highly convective. So Bukov length going from 5 meters all the way to 300-400 meters. So what do we do about that? So we did some simple dimensional analysis. So in our basic framework, without convection, we have this sort of a functional relationship, okay. And when convection becomes important, we would expect W star, the convective velocity scale, to come into picture. But convective velocity scale will give you an idea of how strong the convection is. But you also need a scale for how strong the advection is. Okay, and then only you can talk about the competition between the two. That's what Richardson number does. So we said that, okay, let's have, we were having radio sonde data. So from radio sonde, what do we get? So we can have a bulk velocity in the boundary layer as a measure of advection. So UB is bulk velocity, and then the ratio W star by UB is really telling you something about convection and advection. So these numbers we could get from the sonic anemometer and radio sonde profiles. And here is just once, if the boundary layer winds are weaker, then it's going to be more convective. Okay, if the winds are stronger, then it's going to be less convective, provided you measure at the same time of the day. So this is what is seen here. Solapur and Mehboob Nagar radio sondes were launched around 11 a.m. to 2 p.m. So roughly the same time. So you can see that this UB is reasonably well correlated with Z by L. So this is a good measure of convective effects. Now, see, convection is also like a boundary condition here, because it is the surface flux, heat flux, right? So it's a boundary condition. So our basic scaling coming from dynamics, we have to top up with boundary condition correction effects. So we topped up this scaling with W star by UB effect, okay, and then fitted the same model, and then that dramatically reduced the scatter in the predictions. So now we can predict it much better compared to the U star. There is also some work which I will not show now because we don't have much time, which can tell you what W star itself is. Okay, so it turns out that, so what is the bottom line? You give me a radio sonde profile, I will tell you within some uncertainty, I will tell you what the surface layer momentum flux and heat flux is. Okay, so that's the bottom line. And these are very fresh, like for past 2-3 days I have been crushing Abhishek to crunch numbers on the computer. So this is a very remarkable result that we have got. So these are idealized WRA various points, and how the simulations are carried out, that is written here. Essentially, these are the laboratory boundary layers that we already published. This is the model which is fitted in our physics of fluids paper. Okay, this model is not fitted to WRF data. It is fitted to our physics of fluids paper laboratory data points. And WRF simulation is done with surface roughness almost tending to 0, and surface heat flux switched off, so that it replicates, and the background temperature profile is uniform, so that it replicates approximately the laboratory conditions. And you can see that these points remarkably fall on this line. So this is actually the proof of the concept that this kind of a model can really be extended to include scales which are of interest to atmospheric scientists. So yeah, this is what it is. And then these are the acknowledgements. Setting up this kind of a lab would not have been possible without the support of all the directors of IITM, the ministry, of course the project director, team members, and various people. Like, setting up a lab is not like, you just work alone. It's not like that. You work with so many people. You have interactions with, so all sorts of teleconnections are there. And you need a positive feedback from all the teleconnections to make the things work. So I'm really honored. To get this award. Professor Pisharoty is a big name, and it brings a big responsibility on us. And I can assure you that we will try our best to live up to that responsibility. Thank you.